Our next topic in metals and non-metals chapter is chemical properties of metals. We have covered up the physical properties of metals. So now we are doing the chemical properties of metals. So first property here is reaction of metal with oxygen. So when we say oxygen, actually it is air only that we are using, and from air oxygen will be used for the burning. So heading we are writing oxygen, but remember what we are using here is for burning. When anything is kept outside for burning, it is actually reacting with the air, and from air that substance uses oxygen actually for burning. So when metals are burnt in air, see a word I've written here is air, then what will happen? This formation of metal oxides. Metal oxides are formed by most of the metals, because some metals they don't even burn in air. So by most of the metals this reaction is shown, and reaction is metal, in words I'm writing first of all, metal plus oxygen. Again we will not write air here, we write oxygen, because actually from air what is used here is oxygen. Here if you want to mention, you can mention air here, and it forms metal oxides. Now reactivity of all metals is not same with oxygen. Some metals are more reactive. Reactive metals, if we take, that is sodium or potassium, these are very reactive metals. Reactive metals, they react at room temperature. We just have to keep them outside. We will not do anything. On their own, these metals, they will start burning. So reaction here is, if I take sodium, it's Na, reacts with oxygen and it forms sodium oxide. Its formula is Na2O. To balance it, we are writing 4 and 2 here. Similarly, if I take potassium here, then it will be potassium potassium oxide that we'll get here. So this is about sodium and potassium. Now I'm taking the example of aluminium here. Aluminium burns, but only on heating in air. It will not burn on its own at room temperature. We have to heat aluminium metal, and then only it will react with oxygen of air, and this also forms aluminium oxide. Again, to balance this, 2 and 4 will come here. Next, after this example of iron and copper, I'm taking iron and copper, they do not burn in air. See what I'm writing here is do not burn in air, even on strong heating. Like aluminium can burn on heating, but iron and copper do not burn in air even on strong heating. But these two metals, they react with oxygen. Just pure oxygen will not take air here. So if oxygen is taken here, then they will react and they will form oxides. So again they will form oxides only, but for the reaction pure oxygen is required here, not air. So copper reacts with oxygen. I'm writing the reaction of copper here, and it forms copper oxide. So these metals also are forming oxides. But some of the metals, they do not react with air, and these metals are less reactive metals. That is why these are called less reactive, because they are not reacting, they are not burning in air. And examples of less reactive metals are silver and gold. Do not react with oxygen even, and even at high temperature, if we'll burn them, then also they will not react. So that is why these two metals are examples of very less reactive metals. After doing this property that metals, they burn in air or with oxygen and they form oxides, next we are coming to what is the nature of these oxides that we'll get. Metal oxides that we get after burning in air, what is the nature of these oxides? The oxides formed by most of the metals are basic. Most of the metals are basic in nature. Example of these oxides are, like if we'll take sodium oxide, potassium oxide, magnesium oxide, copper oxide, and many more examples are there. So metal oxides, they are mostly basic in nature. Why we say they are basic in nature? Because when we add water to these oxides, what is added? Water is added, they dissolve completely. So they are completely soluble in water, and the solution that we'll get of the oxide in water, this solution is basic because it turns the red litmus to which color? To the blue color. So we know that a solution changes red litmus to blue color, that solution is actually basic in nature. So why these oxides are basic? Because their solution in water actually is basic in nature. So I have written here most of the metal oxides are basic. There are some oxides of metals like Al2O3 and zinc oxide. These are amphoteric in nature. Amphoteric in nature. What is the meaning of amphoteric? Amphoteric means that these oxides, they show both acidic and basic behavior. Both acidic and basic behavior. That is why these are amphoteric in nature. Now, very important question we have after this is, we have to prove that aluminium oxide or zinc oxide, we can take that these are amphoteric in nature. So how we prove this thing that this oxide is amphoteric in nature? They show both acidic and basic behavior. That means they react both with acid and with a base. So if I take aluminium oxide and react this with acid or react this with a base, it is reacting with acid as well as with a base. So in this case, when it's reacting with acid, this is acting here as a base. Base and acid, they react to form salt and water. So because here it is forming salt and water by reacting with acid, and we know base only reacts with acid to form salt and water. That means in this reaction, this is acting as a base. Now in this reaction, when we react this with a base, it is again forming a salt. This salt is sodium aluminate. Sodium aluminate salt plus water. So this is a new salt for you that you haven't studied before. Sodium aluminate. Again, salt and water is formed, and here it is base. That means this one is acidic here. So aluminium oxide is acting as base as well as an acid. That shows that aluminium oxide is actually amphoteric in nature, and reactions we have to balance here. So this is the answer for this question, that aluminium oxide is actually amphoteric in nature. So this is about the first property that we have done, reaction of the metals with the air or with oxygen. Now we're coming to the second chemical property of metals, and this chemical property of metals is reaction of metals with water. Reaction with water. Metals, they react with water, and what they produce? Metal with water. They form metal oxide, but now here along with this there is hydrogen also. And this metal oxide, if we further add water to this metal oxide, and this oxide should dissolve in this water, then what we get here is metal hydroxide. See both the reactions, it's metal with water. We get metal oxide and hydrogen. But if we take metal oxide and add water, what we get here is a metal hydroxide. Now again, some metals are more reactive, some are less reactive. So here the reaction is with the cold water or with the hot water or with the steam will take place. So very reactive metals are sodium and potassium. They react with cold water. There is no need even for a hot water or a normal water. Cold water, with that also they can react. Then if we take magnesium, it do not react with cold water, but it reacts with hot water. Then only reaction will take place. That shows that magnesium is less reactive than sodium and potassium. And if we take iron, iron does not react even with hot water, but it reacts with steam. So this shows that iron is less reactive than magnesium. But there are some metals like lead, copper, silver, gold, platinum. These are very less reactive metals. They do not react with water at any condition, whether it's a hot water, cold, steam. They will not react with the water at all under any condition. Now, if I take metals like the sodium and potassium, these metals they react with, just see the difference here, metal plus water. I have written here metal oxide, but now see what I'm writing here is metal hydroxide plus hydrogen. Here is metal oxide, here is metal hydroxide. So how the two reactions are different? This is only if it is very reactive metal like sodium and potassium. Because they're very reactive, they can further change the oxide to the hydroxide. So there are so many things that we have to learn in this thing. For sodium and potassium, metal hydroxide. For other metals, it's metal oxide and hydrogen. And to metal oxide, if we add water, then we get metal hydroxide. And water can be cold or hot, or it can be steam. That depends on the reactivity of this metal. So I'm taking examples here. Like here we have taken sodium and potassium. So first example I'm writing is sodium reacts with water. And this formation of sodium hydroxide plus hydrogen, but lot of heat is evolved during this reaction. That shows that this reaction is highly exothermic in nature. We say that sodium and potassium reacts violently with the water. They react violently with water. The word that we use here is they react violently with water. Now after sodium and potassium, I'm coming to calcium. Calcium also with the water, it forms calcium hydroxide. So here I'm adding calcium, potassium, and even the calcium I'm adding here. So even the calcium reacts with the water and forms calcium hydroxide and hydrogen. But it can react with the cold water. It can react with the cold water here, and reaction is less violent. With sodium and potassium, reaction is more violent. With calcium, if we do a reaction, we will get hydroxide, but reaction is less violent. So example of calcium I'm taking. It reacts with water to form hydroxide, plus there is hydrogen here. This is cold water. There's no need for hot water. With cold water only it can react, but reaction is not so violent. But one thing I'm adding here is calcium floats on the surface of water. So when we are doing this reaction of calcium with water, calcium floats on the surface of water. So why it floats on the surface of water? Because it becomes very light in water. Reason is, when this reaction is taking place, hydrogen evolves. So actually the bubbles of hydrogen gas, they stick to the metal. Because of this, calcium becomes very, very light. As the bubbles of hydrogen gas formed, they stick to the metal. So this is about the reaction of the metals with the water. They are forming metal hydroxide, plus they are forming the hydrogen also. But then I told you some metals, they form the oxides also. Very reactive metals like sodium, potassium, calcium, magnesium, they are forming the hydroxides, and other metals, they are forming the oxides. So now we come to these metals which are forming oxides with water. Some metals like aluminium, zinc and iron, they do not react with cold or hot water, but they react with steam. They react with steam. That shows that these metals are less reactive than the sodium, potassium, calcium and magnesium. They react with steam, and these metals, they form the metal oxide. So remember which metals they form hydroxides with the water, that is sodium, potassium, calcium and magnesium. While these metals, aluminium, zinc and iron, with water, that is with steam, they are forming metal oxides here. So it's metal plus water, metal oxide and hydrogen. So beta, first learn the general reactions, and after that you can take these particular examples of the metals, and then you can learn. Water here is a form of steam beta. Okay, so I'm writing the example. Take aluminium, reacts with the water and it forms oxide of aluminium with evolution of hydrogen. To balance this 3 and 3, and this is actually a steam. And aluminium does not react with the water under ordinary conditions. Why? Because on the surface of aluminium there is a passive layer of aluminium oxide. Suppose this is aluminium metal. On the surface of this, there is a layer of aluminium oxide. We say this is a passive layer. Passive means it's not reactive. So because of this aluminium oxide on surface, aluminium is not reacting under ordinary conditions. So aluminium reacts with steam only and not under ordinary conditions. The reason is because there's a layer of aluminium oxide which is passive here. Next example is zinc reacts with steam to form zinc oxide and hydrogen. So here also this one is steam only. Next example here is iron. This also reacts with steam and it forms Fe3O4 iron oxide with evolution of hydrogen. Balancing is like this. This is steam and this compound is called iron 2,3 oxide. There are two types of iron, these with the 2 valency and with the 3 valency. So this 2 and 3 is showing that this iron has both these ions here with the 2 valency as well as with the 3 valency. That is why this is called iron 2,3 oxide. Now one note we have here is sodium and magnesium. They are very reactive metals, and we have done that their reaction with water is very violent reaction and highly exothermic in nature. Lot of heat comes out from this thing. So we cannot store sodium and potassium, like we cannot keep them outside. So that is why we have to store sodium and potassium in a kerosene oil. We cannot keep them outside because they can burn also on their own. They can come in contact with moisture also, and reactions can be very, very violent. So to prevent this thing, these are stored in kerosene. So they are out of reach of oxygen, moisture and carbon dioxide of air. This is about the second property of chemical property of metals. Moving on to the third chemical property of metals, that is reaction with dilute acids. I've written word dilute acid, not concentrated, dilute acid. Metals, they react with dilute acids and they form salts with these acids with evolution of hydrogen gas. So some reactive metals, I can take sodium, magnesium, aluminium, zinc, iron, they are reacting with dilute acids. But very less reactive metals like copper, silver, gold, platinum, they don't react with dilute acids. So here I'm taking the example of sodium, magnesium, aluminium. I can take, like if we reacted with the hydrochloric acid, this dilute acid we take, which salt will be formed here? Since it's chloride we have taken, so this is a chloride salt. Then second example, magnesium. This also reacts with hydrochloric acid to form magnesium chloride. Aluminium also reacts with hydrochloric acid and this formation of aluminium chloride here. All these reactions we have to balance. This is 2, 2 and 2 here. In this case it's 2 here. Hydrochloric acid is 6, 3, 2 and this is 2 here. And copper, silver, gold, platinum, these do not react with a dilute acid. Their reaction with dilute acid, you will put cross here, they do not react with dilute acids because they are very less reactive metals. And now we are coming to this aluminium. Aluminium reaction in the beginning is very slow. Again, the reason for this thing is on the surface of aluminium there is a protective layer, that is passive aluminium oxide layer. So initially the reaction of aluminium with this HCl is also very slow. Next I am taking zinc reaction. Fe reaction also with HCl we can write. This is ZnCl2 plus hydrogen. This is FeCl2 plus hydrogen. And balancing here for both the reactions is just the same. And copper, silver, gold, platinum, these they don't react with dilute acids. So after the reaction with the dilute acids, I'm now moving on to a question here. We have taken hydrochloric acid. Metals do not react with dilute nitric acid. We have written dilute acid but not dilute nitric acid. So question is, why metals do not evolve hydrogen gas on their reaction with dilute nitric acid? In hydrochloric acid, the formula is HCl. There is no oxygen here. But if I take HNO3, there is oxygen. Because of oxygen, it is an oxidizing agent, and nitric acid is a very strong oxidizing agent. So what will happen? Why the hydrogen does not evolve out here? Reaction is there, but hydrogen is not evolving out here with dilute HCl, dilute nitric acid. So in general, when metals they react with HNO3 acid, no hydrogen is evolved. See, I'm taking a reaction like we take, for example, a metal here, M I'm writing here, then I'm writing here HNO3. We were expecting that we'll get metal nitrate here and hydrogen, but this hydrogen is not evolving. What is happening to this hydrogen? Since this is oxidizing agent provides oxygen. So this is actually providing oxygen to this and changes this to water. So if this is oxidizing agent, it itself has to get reduced. So when this one is getting reduced after oxidizing the hydrogen to water, this will form the oxides of nitrogen. Either there will be N2O or NO or NO2 will form here. So this reaction we are not getting like the hydrogen evolution and the nitrates of metal. Instead, the hydrogen changes to water and itself this one is changing to the oxides of the nitrogen. But if we take magnesium, right, this point, this is a note here, magnesium and manganese, they react with very dilute nitric acid. See, a word written here is not dilute nitric acid. I have written very dilute nitric acid. And hydrogen evolves. The reason is very dilute nitric acid is not a strong oxidizing agent. So it cannot oxidize the hydrogen to water here. So that is why these metals are able to react with very dilute nitric acid. So this is about the third chemical property of the metals. We have one term after this, that is aqua regia. What is aqua regia? This is actually acid only. It's taken from a Latin word. In Latin, this means royal water. Aqua regia in Latin means royal water. So we take hydrochloric acid and we take nitric acid and mix these in a ratio of 3:1. That means if 3 ml of HCl we'll take 1 ml of nitric acid, mix the two, that becomes aqua regia, and this becomes very, very strong and is highly corrosive in nature. And mostly this is used to dissolve the noble metals like gold and platinum, which are not very reactive. So they dissolve in the aqua regia. Otherwise they are not reacting, we have done with acids. But these metals will react with aqua regia. They will dissolve in fact in the aqua regia. Now next property, the last chemical property of metals is reaction with metal salts. Now from the above reactions, it is clear some metals are more reactive, some metals are less reactive. So if we take a reactive metal, and this metal we will put into a salt solution of less reactive metal salt solution, then what will happen? The reactive metal will displace the less reactive from the salt solution and will come here in place of this less reactive metal, and less reactive metal will take the place of this reactive metal. So this reaction is actually a displacement reaction that already we have done. For example, if I take, like say A is a reactive metal and salt solution is like your BC. This B is a metal here. This is less reactive and this is more reactive. Now if this is more reactive, it can displace this, can take the place of B. So in place of B there is now A. So this becomes AC, and B is coming in place of A, so this becomes your B. So this reaction will take place here, but for this reaction to take place, remember here this metal that we are taking is more reactive than the metal which is there in the salt solution. To understand this, now I'm taking one example. Let's say we take zinc and add this to copper sulfate solution. Now reaction will take place because zinc is more reactive than copper, so it will displace it. So because of this, now this becomes zinc sulfate and zinc will become copper. So copper plus zinc sulfate. Now the changes in this reaction are copper sulfate is blue in color. This is silvery white in color, zinc. Copper has reddish brown color. And the zinc sulfate is actually colorless. So we are taking a beaker here. In beaker we will take copper sulfate solution. Its solution we have to take, that means this is of which color? The solution is of blue color. So blue color copper sulfate solution we have in a beaker, and in this beaker we will add the zinc here. So this is a zinc metal that will add into this thing. So in the beginning, this is, I'm writing the formula only, copper sulfate, and this is the zinc metal. After some time, what we will see, if new things are there, that means the color of these will change, and what we will observe here, solution here, this becomes colorless now. And this silver color metal, that is silver white color metal zinc, that will start changing to the reddish brown color. So first I am making this solution. This is from the blue, it will become colorless. And the metal that is here, zinc, silvery white metal, this will start changing to the reddish brown color. So when the color will change, that shows that the chemical reaction has taken place. So as a result of this chemical reaction, now this solution has changed from blue to colorless because this is now zinc sulfate, which is colorless. And the metal from this silvery white color, that is zinc metal, will change to reddish brown color, and reddish brown color metal here is copper. So these changes will take place because the displacement has taken place. So this is a chemical reaction that is taking place, but this can happen only if the metal here is more reactive than the metal which is in the salt solution. So this is one example of reaction of the metals with the metal salts. One more example I'm taking for this thing, example 2. If we take, for example, iron metal, and to this we add copper sulfate. Now, even here, iron is more reactive than copper, so it will displace the copper. Copper will take the place of the iron, and iron will take the place of copper. And as a result of this reaction, we will get FeSO4, and copper metal will come out from this. Now, the change in the colors here, this Fe is a grayish black color metal. Copper sulfate solution we know is blue in color. Copper metal we know this is reddish brown in color. And ferrous sulfate, this has a very light green color. A light green color solution will form. From blue it will start changing to which color? It will change to a light green color. So here if we'll show this thing, the change in the solution color and the metal here, in the beginning we have taken a blue color solution, that is a copper sulfate. So this I'm taking is a copper sulfate, blue color. And the metal that we take here is, that is the iron, which is a grayish black color metal. So I'm taking the grayish black color, making it little black. Like this. And after some time what will happen? Metal taken here is iron, and the solution here is copper sulfate. But after some time we will see the color will start changing from the blue to a light green color. A light green color solution we will see. And the color of the metal, this one will start changing to the reddish brown color. A reddish brown color metal we will see here. The reason is because this solution now is ferrous sulfate, which is light green in color. So from copper sulfate it has changed to ferrous sulfate. And this metal from iron has changed now to copper, which is reddish brown in color. That means chemical reaction has taken place. So iron is more reactive than copper. That is why this is possible. Now one more example here to understand this is, if we take copper and react this with silver nitrate solution. In this case, again copper is more reactive than silver, so it will displace the silver, and this will become now copper nitrate, and silver will come out from this. Copper nitrate formula is CuNO3 whole twice. So to balance this equation, actually this has to be 2AgNO3. Along with copper nitrate, we are getting silver. So to balance the silver, we have 2 here. Color of copper we know is reddish brown. And silver nitrate is approximately, this is colorless only. Silver, that is silver in color, so grayish white color, you can write grayish white color metal. And copper nitrate, like copper sulfate, is blue in color. So changes here are, initially we have a colorless solution here. a colorless solution. And in this, the metal that we'll add is a reddish brown color copper metal. So a reddish brown color metal I'm taking here, just to make it little brownish. So labeling of this part, this is silver nitrate solution, colorless, and this is copper metal. And after some time, what will happen here? We will see that a solution from colorless will start changing to blue color. So this colorless solution will become blue now. And the metal from reddish brown color, it will start changing to grayish white color. Grayish white color. Hope this is visible. So labeling of this part is, this is which metal? Silver, and this is copper nitrate. So when we'll say a change in the color of the solution or the metal or both these things, that means a reaction has taken place here. So most of these examples that have taken, the color is changing in these displacement reactions. But only thing that we should know is this metal should be more reactive than the metal in the salt solution. If we do it the other way, like here I take copper in the beginning and here I'll take the parasulfate, here reaction will not take place because copper cannot displace iron from the salt solution, as copper is less reactive than iron. Similarly here, if I do the reaction by taking silver and copper nitrate, then reaction will not take place here because silver cannot displace copper, as silver is less reactive than copper. So for these kind of reaction, we should know which metal is more reactive, which one is less reactive. So that will cover up in the next topic.